This presentation will introduce and discuss telescoping sums. It will include explanations of why the method works, why it is useful, and also explain a range of examples. It will begin with basic instances and examples, then work its way towards less intuitive examples of a telescoping series. This presentation is brought to you by Group B14, which is comprised of members T.J. Bierce, Matthew K. Berger, Zach Houston, and Ryan Kreider. This video, along with others covering various topic areas of discrete math, can be found on knoatom.com. That's knoatom.com. First, we'll discuss what exactly a telescoping sum and what is meant by the name of telescoping series. In a telescoping sum, consecutive terms cancel each other out. The result is the first term minus the very last term, and these telescoping sums take the form the sum of I equals 0 to n of ai plus 1 minus ai. In this way, a telescoping sum is thought of as a series of terms where the first term and the last term are all that remain once the summation is taken. This is done by looking at examples where each of the terms in the middle cancel each other out by being both added to the series and subtracted from the series as the sum progresses. But why exactly is it thought of as a telescope? The reason that it is thought of as a telescope is because you can look at it as being the very first and the very last term. In this way, it's like a telescope where you can fold it together and only the extra outer edges actually make an impact on the summation. Let's do an example. The summation from I equals 0 to n of ai plus 1 minus ai. That's the same summation that you saw on the last slide, and here we're going to go into more detail of why this abstract generalized telescoping sum works the way that it does. This summation is equivalent to a sub 1 minus a sub 0 plus a sub 2 minus a sub 1, continuing on until the nth term, where it is a sub n minus a sub n minus 1 plus a sub n plus 1 minus a sub n. In this way, you can look through the terms and see that there's various terms that are canceled out. Looking to the beginning, you see that a sub 1 and is both added to the summation and removed from the summation by subtracting a sub 1. This pattern continues throughout the telescoping series to leave you only with the beginning element and the very last element. Notice that the terms appear twice with opposite signs. These terms are going to cancel, leaving only a sub n plus 1 minus a sub 0. An easy example. This example is included to give you a better understanding of exactly how a telescoping series works. It's designed to provide a very basic example to underpin the rest of the examples, which will get progressively more difficult and hopefully complete your understanding. We're going to try to find the summation of I equals 0 to 4 of I plus 1 minus I. If we expand this out, we get the result that 1 minus 0 plus 2 minus 1 plus 3 minus 2 plus 4 minus 3 plus 5 minus 4. This can be arranged to result with 0 plus and then 1 minus 1. Then we have 2 minus 2. Then we have 3 minus 3. Then we have 4 minus 4, and lastly we just add 5. If you simplify this down, you will see that all the middle terms cancel out because they're both added and subtracted from this series. This therefore simplifies to 5 minus 0, which is equivalent to just 5. Now we will look at a slightly more difficult example to hopefully increase your understanding. This is a summation from I equals 0 to 4 of 2i plus 1 minus 2 to the I. The correct answer to this summation is 2 to the 5th minus 2 to the 0, which is 32 minus 1, which is equivalent to 31. This is done because when you look back at the summation, you will see that only the first and last terms matter. To achieve the first term, you will plug in 4 to the first term in the summation, which is 2 to the I plus 1. So you get 2 to the 4 plus 1, 2 to the 5th. The last term, what's subtracted from the summation at the end, at the very last element, is 2 to the I. And we use the 0th term because the summation begins at I equals 0. So you have 2 to the 0, and lastly you have 2 to the 5th minus 2 to the 0. Is that the answer that you got? Now we'll explain why this works. Looking back to the expansion rationale from the previous slide, the telescoping sum of the summation from I equals 0 to 4, the same sum as you saw before, can be seen as its first term, 2 to the I plus 1, minus its last term, 2 to the 0. which is equivalent to 32 minus 1 equals 31. This occurs because the other terms will cancel, that is, they are both added and subtracted to the summation. Now we look at a variation on the telescoping summation. This example is far from intuitive, but if we give provided a hint, which will make the example much more easy to follow, and will explain why it is so useful. You are initially presented with the following summation: the sum from k equals 0 to n of k times the value k plus 1. This is rather difficult to solve. Just looking at it, it's not immediately apparent that this summation is a telescoping sum. However, there is a way that it can be transformed to be a telescoping summation, which makes it much more simple to solve than taking the summation out term by term or using a calculator. If you are given the hint that k times k plus 1 times k plus 2 minus k minus 1 times k plus 1 is equivalent to 3 times k plus 1, then it becomes much easier to solve. Notice here that if you look to the right side of the equation, of the equals sign towards the bottom of the slide, you will see that there's simply 3 times the value that the terms are summed over. Later on, this will make it easier to see why we divide the left side by 1/3 to get the result that we are looking for, which is a more simplified version of the initial summation presented on the slide. This is a continuation of the previous example. It becomes clearer that the original summation is equivalent to the sum from k equals 0 to n of 1 over 3. Remember from the last slide that we are dividing it by 1 over 3 from the right side to make it equivalent to the original summation. So it's 1 over 3 times k plus 1 times k plus 2. Then we subtract the next term in the series, which is we subtract k minus 1 times k times the value of k plus 1. If you take the second term and plug in k plus 1, you will get the first term. For k plus 1 minus 1 times k plus 1 times k plus 1 plus 1 is equivalent to k times k plus 1 times k plus 2. The reason why this is valuable to do is because when you add k plus 1, you're going to get the term immediately prior. So in this way, the right term is the one immediately following the term on the left. This shows clearly that we are now dealing with a telescoping summation. Further continuation. Following the logic of a telescoping summation, it will be n times n plus 1 times n plus 2 for the first term. Then when 0 is plugged in for the second term, it will be 0 times negative 1 times 1, and anything multiplied 0 will just give you the output of 0. This result, when divided by 3, gives you the result 1 over 3 times n plus 1 times n plus 2. One last hurrah / example. We are going to work with the summation from n equals 1 to infinity of 1 over n squared plus n. Finding the summation involves splitting into partial fraction. This step is useful for finding the summation, but functionally you don't have to know this for telescoping series. However, with this example, it makes it significantly easier. This is done by 1 over n squared, and then breaking this into a over n plus b over n plus 1. If you do the partial summation, you will find the value of a equal to positive 1 and the value of b equal to negative 1. And doing this, we get 1 over n minus 1 over n plus 1. When you see the summation in this formation, it should become much more clear as to how this relates to a telescoping series, because we have a term minus the following term in the series. Looking to this in its final summation, we have the sum of n equals 1 to infinity of 1 over n minus 1 over n plus 1. This is equivalent to 1 over 1, which is just 1. That's the very first term in the series if you look to the left. Then you subtract from this 1 over 2, which is the following element in the series. Then you add 1 over 2, then you subtract, and then you add 1 over 2, then you subtract 1 over 2, then you add 1 over 3, then you subtract 1 over 3. This continues until you get to the nth term, where it's 1 over n minus 1 over n plus 1. In this way, the 1 over n will have canceled from the term prior to it, but the 1 over n plus 1 will not have. Following from this logic, you will see that this summation is equivalent to 1 over n minus 1 over n plus 1. Now for some additional reading. This is a convenient way and the reason and explanation of why the series is a telescoping series. If you look at the telescope presented in the image, you will see that the right side of the telescope can be thought of as the last term and the left side as the first term. Those are the only relevant terms when you use the telescoping series. In this way, the clip font that you just saw is a convenient way to remember a telescoping series. That's all, folks. Again, if you are looking for this video or any others like it, be sure to check out the site knoatom.com. That's knoatom.com. That site contains videos on probability, on counting, on sequences and summations, and on various other aspects of discrete mathematics. Thanks for listening.